Hello and welcome back. Today we're going to learn about another single-digit pattern before we delve into the more complex wings, chains, and loops. I'm talking about empty rectangles. This is a very commonly occurring pattern, and it is one of my personal favorites. The logic behind them is very interesting, and it will give you a nice foundation to the logic behind some of the more complex techniques that we will learn about in future lessons. You have to have a vivid imagination to see these because they can take on many different shapes, just like a chameleon changes colors. But once you know what to look for, it will be a piece of cake. Don't worry. I highly recommend that you watch this video all the way through to the end because later on I'm going to show you something that is really cool and that has some very peculiar logical implications. It involves an interesting phenomenon about conditional statements with regard to a special kind of empty rectangle that will come into play when we talk about discontinuous loops and other complex chains later on in the course. So stay tuned for that. But for right now, let's go over to the puzzle board and see all the different ways that empty rectangles can show themselves and how they work. Okay, before we begin, I would like to remind everyone that the stripped down, hand-drawn diagrams that you quite often see at the beginnings of most of my tutorials are not real puzzles, and they are not meant to be solved or critically analyzed. They are for demonstration purposes only. So please disregard any random naked singles, X-wings, locked candidates, or any other unrelated pattern you might notice, and instead try to focus only on the particular point I am trying to make. Okay? Great. An empty rectangle occurs whenever a particular candidate is situated in only one row and only one column of a particular block. Okay, let's see what this means. For instance, in this diagram, with respect to block 2, candidate 3 lies only in row 1 and column 6. As you can see, there are 5 cells that take up row 1 and column 6 within block 2 that I have colored in green, which leaves these 4 other cells where candidate 3 does not appear. This is the empty rectangle, these aqua-colored cells. And this is where the pattern gets its name. So the empty rectangle is actually where the candidates of our focus are not located. Got it? Their orientation leaves an empty rectangle. It's a little bit odd, I admit, but that's what this pattern is called, an empty rectangle. Here it is actually a square, but it does not always take this shape. For instance, down here in block 8, if candidate 3 was only in row 7 and column 5, it would look like this. And thus, in this case, the 4 remaining cells would indeed form a rectangle. And again, those aqua-colored cells form the empty rectangle where our candidate of focus is not located. If you remember from geometry class, a square is a specific kind of rectangle. So all squares are rectangles, but not all rectangles are perfect squares. In any event, one row and one column will always occupy exactly 5 cells in any given block, and the remaining 4 cells will form a rectangle of various shapes. This is the empty rectangle. The particular candidate you are looking at does not need to be in all 5 of those green cells for this technique to work. It just needs to be located in only one of the rows and only one of the columns in a particular block. For instance, if it looked like this, candidate 3 would still be in just row 1 and column 6. And likewise, if it looked like this, candidate 3 would still be in row 1 and column 6. So before we talk about the actual solving technique, The first thing we need to do, and it is very important, is that we have to be able to recognize and identify all the different configurations this pattern can take. And believe me when I tell you, there are a lot of them. As it turns out, there are 33 different shapes that you will need to be able to see. The first one looks like this. Let's call this the right angle. And the right angle has 4 possible rotations, like this. Each one is turned 90 degrees. But as you can see, candidate 2 only occupies 1 row and 1 column within each of those 4 blocks. Then we have something that looks like the letter T. So let's call this the T. The T also has 4 possible rotations. Each one is turned 90 degrees. Okay? And then we have the cross. And as you can see, the cross has only 1 rotation because whichever way you rotate it, it looks exactly the same. It will always be the middle column and the middle row of any block. That will form a cross. Now these next ones are a little tricky because they can be perceived in numerous ways. But basically, here is what they look like. The first one of these patterns looks like the letter L, and the L has 8 possible rotations. 4 in green, as you see where the 3 cells are on the edge of the block, and another 4 in the color aqua, where the 3 cells are in the center of the block. And then we have a backwards L, which kind of looks like a periscope. So let's call it the periscope, for lack of a better name, like on a submarine. And the periscope also has 8 possible rotations, just like the L. It's the mirror image of the L. The ones in green, where the 3 cells are on the edge of the block, and the ones in aqua, where the 3 cells are in the center of the block. And lastly, we have what looks like a short letter T. And I have been trying to figure out what we should call this one. I thought of a mushroom or a thumbtack. So let's go with thumbtack, okay? The thumbtack also has 8 possible rotations, just like with the L and the periscope, and they look like this. The green ones are where the 3 cells are on the edge of the block, and the ones in aqua where the 3 cells are in the center of the block. But notice that when the 3 cells are on the edge of a block, the thumbtack acts exactly like a T, like this one up here in block 1. That's the same as a T, and you can do that with all of them. Okay? And then when the 3 cells are in the center of the block, it acts exactly like a cross. Those all can be perceived as a cross. And likewise, with the L or the periscope, when the 3 cells are on the edge, they act just like right angles. You see? And when the 3 cells are in the center, they act just like a T. So really, if you remove those duplications, there are really only 9 basic shapes, which makes sense because if you think about it, there are 3 rows and 3 columns in each block, and 3 times 3 is 9. Like if you called the rows A, B, and C, and called the columns 1, 2, and 3, you would have A1, A2, and A3, then B1, B2, and B3, and then C1, C2, and C3. Again, 9 possible combinations of 1 row with 1 column. But because we're dealing with various distributions of candidates, i.e. there won't always be an instance of our candidate in all 5 cells, and to see these shapes in puzzles, it really helps to be familiar with the 33 different subshapes, if you will, that I just showed you. There are 8 shapes with 4 rotations each, and then we have the cross with just 1 rotation. So that totals 33. That's not too bad, is it? With a little practice, you'll begin to see all of them quite easily, I'm sure. But notice that if we count all the various ways that the candidates can be positioned to form these 33 shapes, like if we count this one in block 1 and this one in block 2, which are now slightly different, if we count those as two distinctly different configurations and then take into account all their rotations, then there are probably well over 100. I did not take the time to count them because it is quite an intricate and tedious task, and it serves no purpose to know exactly how many there are. If you want to figure it out on your own and you come up with the correct answer, please notify me by email, as I would be interested to know. But please be sure to send me your proof. Ha ha. In any event, all you need to know and be able to recognize are those 33 shapes, and just know that the particular candidate does not need to be in all 5 cells, as long as it is situated in just one row and just one column in the particular block. Okay? Great. So let's go through them one more time. In block 1, we've got the right angle, and that has 4 rotations. In block 2, we have the T, and that also has 4 rotations. In block 3, we have the cross, and that only has 1 rotation because each rotation looks the same. In block 4, we have the L, where the 3 cells are on the edge, and that has 4 rotations. And then in block 5, we have the L, where the 3 cells are in the center, and that has another 4 rotations. Then in block 6, we have the periscope, where the 3 cells are on the edge, and that has 4 rotations. And in block 9, we have the periscope, where the 3 cells are in the center, and that has 4 rotations. In block 7, we have the thumbtack, with the 3 cells on the edge, and that has 4 rotations. And in block 8, we have the thumbtack, where the 3 cells are in the center, and that has 4 rotations. Another way to look at this is by saying the rows are A, B, and C, and the columns are 1, 2, and 3 in each block. So with that in mind, in block 1 we have A1, in block 2 we have A2, in block 3 we have A3. And then in block 4 we have B1, in block 5 B2, in block 6 B3, and then in block 7 we have C1, in block 8 C2, and block 9 C3. Those are the 9 possibilities. But if we take a closer look at this diagram and color it a little differently, we can see that blocks 1, 3, 7, and 9 are the 4 rotations of the right angle, and blocks 2, 4, 6, and 8 are the 4 rotations of the T, and block 5 is the cross. These 9 shapes encompass all the 33 shapes, but most of the time they don't look exactly like this in puzzles, which is why you need to be able to recognize an upside-down periscope or a sideways thumbtack when you see one. So it's a good idea to familiarize yourself with all of the possibilities. Capiche? And remember, the candidate that we're looking at does not need to be in all of those colored cells. It just has to occupy one row and one column in any given block. All right, so now that we have that straight, let's see how this pattern helps us eliminate candidates that are proven to be false. All right, let's say we have an empty rectangle pattern here in block 2 where candidate 3 lies in row 1 and column 6. And let's say we have a conjugate pair down in row 7 where the candidate 3 in the blue cell lies in column 6, which is the column of our empty rectangle. So let's look at the 2 cases for the candidate 3 in the blue cell. It's going to be either true or false, right? Okay, if it's true, and we fill it in, and that wipes out all the 3s in column 6 because that can be the only 3 in column 6. And so what happens is, in our empty rectangle, all that's left are these 2 3s up in row 1, and they become locked candidates because there are no other 3s in that block, and that would have to eliminate this candidate 3 in the red cell in row 1, column 2. That would be false. All right? Now let's go and do it the other way. Let's say the candidate 3 in the blue cell is false But now because we have a conjugate pair down here, that means the candidate 3 in the yellow cell has to be true. And so if it's true, again, it eliminates the candidate 3 in the red cell. So the candidate 3 in the red cell is false either way, and it can be eliminated. It's a verity because both cases for the candidate 3 in that blue cell lead to the same conclusion, that candidate 3 in row 1, column 2 is false. Now notice that if we move the yellow 3 over to the other side, like this, the same thing happens. If the blue 3 is true, it wipes out the 3's in column 6 and leaves these locked candidates in block 2, which forces the 3 in the red cell to be false. And if the candidate 3 in the blue cell is false, then the 3 in the yellow cell will be true, and the 3 in the red cell, again, will be false. So now let's see what this looks like when one of the candidates of the conjugate pair lies in the row of the empty rectangle. It's the same thing. In this diagram, if the candidate 3 in the blue cell is true, then that leaves a naked single here in row 3, column 6, and that has to be true, which makes the red 3 false. And if the 3 in the blue cell is false, then again the 3 in the yellow cell will be true, and that will negate the 3 in the red cell once again. But notice that this is only going to work if the blue 3 and the yellow 3 are in two different blocks. Because if this 3 was up here, then because that's a conjugate pair in column 1, the blue 3 and the yellow 3 become a set of locked candidates, which would allow you to eliminate those 4 other candidates in block 1, but it would have no effect on the empty rectangle or the candidate 3 in the red cell in row 5. All right, so now we can make this generalization. Once you see an empty rectangle pattern, then find a conjugate pair A and B that lies outside of the empty rectangle block such that candidate A lies in the same column as the empty rectangle. And candidates A and B must lie in different blocks. Then candidate C can be eliminated if it lies in the same row as the empty rectangle and can also see candidate B. And of course, you can swap the words column and row, and these same rules will apply. Got it? Great. But now for the oddities. So fasten your seatbelts. Let's take a look at what happens when there are only 2 candidates that form the empty rectangle pattern, i.e. when there is only one candidate in a row and another candidate in a column of a particular block, and they are the only 2 instances of that candidate in that block. There are 4 ways that this can happen. 1, where the 2 candidates are in opposite corners of the block, like that. And 2, where one of the candidates is in a corner and the other is on the edge. And 3, where the 2 candidates are on 2 different adjacent edges of the block, like that. And 4, where one of the 2 candidates is in the center and the other candidate is in a corner, like this. Notice that it cannot be like this, or it cannot be like this. That would not qualify as one candidate being in a row and another in a column, so forget about that. All right, let's take a look at block 1, where the 2 candidates are in the 2 corners. We can see this as a right angle, like that, but we can also see it as a right angle the other way. It works both ways. So when you see this configuration, your candidate A of the conjugate pair can be down here in column 3, or it can be up here in row 1. And then if you see it the other way, it can also be in column 1, or it can be in row 3. So that doubles your chances of finding a candidate elimination. And over here in block 3, where you've got one in a corner and one on the edge, you can see this as a right angle, or you can see it as a T, or you can see it as a periscope this way, or you can see it as a periscope that way. And if this 7 were down here, you could see it as an L that way, or an L that way. So these things are like chameleons. And then down here in block 7, where the two candidates are on adjacent edges, you can see this as a right angle, or you can see it as a periscope, or you can see it as a thumbtack that way, or you can see it as a thumbtack that way, or you can even see it as a cross. And then over here in block 9, where we have one in the center and one in a corner, you can see this as a thumbtack this way, or a thumbtack that way, and also a T like that, or a T the other way. So these things take on so many shapes that it gives you a ton of opportunities to find a conjugate pair that will match up and allow you to find a candidate elimination. All right, there is one more special case for these, but let's look at some real examples first, and then we'll talk about this one other oddity a little bit later. Okay, what we're going to do is we're going to color the candidates of the empty rectangle green, and we'll color candidate A of the conjugate pair blue, and that'll be the one that's in the same row or the column as the empty rectangle. And then its partner candidate in the conjugate pair, we're going to color that yellow, and that'll be candidate B. And then candidate C we'll color in red, and that will be the candidate to be eliminated. And in this first puzzle, we'll go through the logic, and then after that, we'll just run through them a little more quickly. Okay? All right, so here on candidate 9, let's light them up. And we see in block 8, we've got a T. So here is our T. There's your empty rectangle. And we look up in row 1, and we've got a conjugate pair. There's candidate A, and there's candidate B. And then we look in row 7, and we see there's a candidate 9 in there that can see candidate B, and it's in the same row as our empty rectangle. So that can be eliminated as false. Now, if the 9 in the blue cell were true, then that would negate all the rest of the 9s in column 5, which would leave a set of locked candidates in row 7, which would eliminate the 9 in the red cell. And then, if the 9 in the blue cell were false, that would make this 9 up here true in the yellow cell, which would negate the 9 down here. So this 9 in the red cell would be false either way. All right, let's go to the next one. Okay, here on candidate 8, we see that in block 9, we've got 2 8s that are on a diagonal, and I've got news for you. When you see that, you know that there's going to be some kind of an empty rectangle. Because if they were not on a diagonal, then they would either both be in the same row or the same column. So we know we've got one here, and because these are like chameleons, when there are only 2 candidates in the block and they're on a diagonal, you can turn them inside out. So we can see this as a thumbtack like that, or we can see it as a thumbtack like that. Now, the first thumbtack doesn't produce anything because there are no conjugate pairs that are either in that row or that column. But if we do it the other way, we see we've got a conjugate pair over here in column 1 that starts in the same row as the empty rectangle. So there's your candidate A, and there's your candidate B. And so the candidate to be eliminated will be the candidate that's in the same column that can see candidate B in the yellow cell, and that's right there. So that 8 is false. But here's something else to point out. This is not only an empty rectangle. Whenever you have 2 candidates in a block on an empty rectangle, it will also be a turbo fish. So let's take a look and see what that looks like. We've got a turbo fish that starts here, and there's a strong link, and then there's a weak link, and there's a strong link. And now this 8 can see both ends of that chain, and so that is false. So that is false by way of a turbo fish, and it is false by way of our empty rectangle. Okay, let's go to the next one. Okay, here let's take a look at candidate 3. And we see in block 4, we've got a thumbtack. Or we can look at that like a cross or a thumbtack. Either one, it doesn't matter, even though there's not a candidate 3 there. Here are the 4 candidate 3s. They form a thumbtack. And now let's see, we've got a conjugate pair in column 7 that starts here and goes there. And this candidate 3 is in the same row as the empty rectangle. And so we can eliminate this candidate 3 in this cell because it can see candidate B and it's in the same column as the thumbtack. All right, let's go to the next one. Okay, here on candidate 1, it looks like we've got a periscope in block 7. Now, when you've got 3 or 4 or 5 candidates in your empty rectangle, it's fixed. You can't turn them inside out. The only way you can do that is if there are 2 candidates. So here we're stuck with the way that is, and we have a conjugate pair in column 4 that goes from there to there. The candidate A is in the same row as our empty rectangle, and that means we can eliminate this candidate 1 up here because it can see candidate B and it's in the same column as the empty rectangle. All right, let's go to the next one. All right, here let's look at candidate 4, and in block 7 again we've got a right angle. And this time we can turn it inside out. It can be that way or it can be this way because there are only 2. You see? But there's nothing to gain from it being this way. But if we fill it in the other way, we've got a conjugate pair up in row 2 that begins there and ends there. And so our candidate C is going to be right here. That is false. You can eliminate that, candidate 4. Okay, let's go to the next one. All right, on candidate 5, it looks like we've got an L in block 4. And there it is. And then we've got a conjugate pair that goes from here to here. And candidate A is in the same column as our empty rectangle. So that means we can eliminate the candidate C over here that can see candidate B. So this 5 in row 6, column 9 is false. All right, next one. Okay, here on candidate 6, let's take a look. In block 1, we've got what you can look at as a thumbtack or a T. It works the same. And in column 8, here's our candidate A, which is in the same row as the empty rectangle. And here's our candidate B. There's your conjugate pair. And this candidate over here in row 8, column 1, is going to be false because it's in the same column as the empty rectangle and it can see candidate B. So that candidate 6 is false. All right, next one. All right, let's take a look at candidate 5 in this puzzle. And in block 3, we've got a T. There's your T. And in column 6, we've got our conjugate pair that goes from there to there, which means we can eliminate this candidate 5 from row 9, column 7. That is false. Okay, next one. In this puzzle, let's take a look at candidate 1, and in block 2, we've got a right angle. And we've got a conjugate pair down in row 6 that begins here and ends there. And our candidate 1 that we can eliminate is going to be in row 1, column 8, because that can see candidate B, and it is also in the same row with our empty rectangle. So that is false. All right, let's go to the next one. All right, let's look at candidate 8 in this puzzle. And in block 1, it looks like we've got a periscope, like that. And we've got a conjugate pair in column 6 with our candidate A, which is in the same row as the empty rectangle, and candidate B down here. And the candidate 8 that we can eliminate will be in row 7, column 3, because that can see candidate B and it's in the same column with the empty rectangle. Now notice this one is also a turbo fish because there are only 2 instances of candidate 8 in block 1. So the turbo fish looks like this. We have, starts there, there's a strong link, and there's a weak link over to this 8 and a strong link down to this 8. So the 8 that's in row 7, column 3 is false because it can see both of the endpoints. So remember, when there are only 2 candidates in the empty rectangle pattern, you can see it as a turbo fish. All right, let's go. Let's do one more. All right, on candidate 7, in block 1, we've got a cross. Now, I don't know what it is, but I think the cross is my favorite. It's nothing religious. I think it just looks cool. It looks kind of like the Swiss Army knife logo. Anyway, our conjugate pair is down in row 8. There's your candidate A and there's your candidate B. And candidate A is in the same column as the cross. And so we can eliminate candidate C that's up here in row 2 because it's in the same row with the cross. And so that candidate 7 is false. Okay? So now, as promised, I want to show you something that's really cool. It's a very special case for these empty rectangles. And not only does this situation allow us to make 2 candidate eliminations, it also allows us to place a digit in a cell. So it is very productive. And the logic behind it is extremely interesting, and that's why I want to show it to you. All right, so let's take a look at that. Okay, I hope you stayed tuned for this because it will be well worth it. Here in block 5, we have a cross with a candidate 3 in all 5 of the cells. But this time, we've got a conjugate pair in row 1 and another conjugate pair in column 2, and they both line up with the cross. This configuration is known as a dual empty rectangle and can be treated as 2 separate regular empty rectangles. So we have 2 candidate A's, and we can look at this from both sides. First, let's look at the candidate 3 in the blue cell in row 1, column 5. If that candidate 3 is true, then that negates all the other 3's in column 5 and leaves these locked candidates in row 5. So one of those 2 3's in the green cells has to be true because those are the only 2 3's left in block 5. So that means the candidate 3 in row 5, column 2 must be false, and you can eliminate it. Okay, but let's put it back in. But now let's say that the candidate 3 in row 1, column 5 is false. Then that means the candidate 3 in the yellow cell, which is our candidate B, that must be true because that's a conjugate pair in row 1. So if that 3 is true, that also negates the 3 in the red cell. So that candidate 3 is false either way. All right, now let's go back. And this time we'll call the candidate 3 in row 5, column 2 our candidate A. All right? So if that candidate 3 is true, that negates all the other 3's in row 5, leaving a set of locked candidates in column 5, which would mean this 3 up here in row 1, column 5 would be false. Okay? That would be false. So now let's do it the other way and say if this candidate 3 is false, then the yellow 3 must be true because that's a conjugate pair in column 2. So if that candidate 3 is true, again, the candidate 3 in the red cell in row 1, column 5 is false either way and can be eliminated. So what we've done is that one at a time we have shown that the candidate 3's in those 2 red cells are both false. And because there was a conjugate pair in row 1 and another conjugate pair in column 2, that proves that the 3 in row 1, column 2 has to be true, and you can enter that immediately when you see this configuration. Okay? Simple, right? But now let's go back to our original position and let's examine the inferences and logical consequences with regard to candidate B in the yellow cell. Understanding this will be a great foundation for understanding the logic of more complex chains and loops later on in the course. So let's take a look and see what's going on here. Let's look at the 2 possible cases for candidate B. It is either true or false, right? That's all it can be. So case 1, if candidate B is true, then that's it. It's true. And case 2 would be that it is false. So if the candidate 3 in row 1, column 2 is false, because that's a conjugate pair in row 1, then this candidate 3 must be true. Okay? So again, that eliminates all the candidate 3's in column 5 and leaves these locked candidates in row 5. So that means this candidate 3 over here must be false. But look, this is impossible because now there is no candidate 3 in column 2 because that was a conjugate pair and now they're both gone. This tells us that the premise of our supposition must be false. If a supposition or a conditional statement leads to an impossibility, then the premise must be false. If my mother was a kangaroo, then I would be a kangaroo. But since I am not a kangaroo, then we know our original premise must be false. Thus we can safely conclude that my mother is not a kangaroo. So if by supposing that candidate B is false leads to what we know is an impossibility, then we know that our premise must be false, i.e., we know that candidate B cannot be false, and therefore we can conclude that it is true. In Sudoku, if we find a supposition or a conditional statement that leads to a contradiction or an impossibility, then we need not go any further. We know the premise must be false. But if the supposition leads to a plausible but undetermined conclusion, then we need more suppositions to complete the picture, because one plausible supposition all by itself does not prove anything. Like if we say, if A is false, then B is true, that doesn't prove anything all by itself. Even though we can count on the logic of that statement, we still need more information to figure out what is really true. Does that make sense? Good. Okay, but let's not stop here. Let's carry it one step further. Since the candidate 3 in row 5, column 2, and our candidate B up in row 1, column 2 form a conjugate pair, there is a conventional strong link between them, right? This means that one of them must be true and the other must be false. They cannot both be true and they cannot both be false. This is the nature of a conventional strong link. So if the candidate 3 in row 5, column 2 is false, which is what the inference just told us, then that means the next inference in the chain is that candidate B in the yellow cell is true. So the net result of the string of inferences is that if candidate B is false, then candidate B is true. Okay? Because if it's false, then the candidate 3 in row 1, column 5 is true. And then that would leave the locked candidates in block 5, which would mean the candidate 3 in row 5, column 2 was false, which would mean that the candidate 3 in the yellow cell in row 1, column 2 is true. I know this sounds crazy, but this is the nature of logic. And what this is telling us is that there are no logical circumstances under which candidate B can be false, because even if we suppose that it is false, it leads us to the conclusion that it is actually true. How about that? This wild concept will come into play in many of the solving techniques that we will cover a little later down the road. The good news for us is that when you see this configuration, you don't have to waste time going through the two halves one at a time, eliminating one candidate C and then the other candidate C. You can simply cut to the chase and immediately enter candidate B into its cell as the correct solution to that cell, now that you understand why. Okay? And when you do that, it will automatically remove candidate 3 from the two red cells. You see? You make all three moves in one fell swoop. Another way to prove this is because that's a conjugate pair in row 1 and a conjugate pair in column 2. If the 3 in the yellow cell is false, then both of those 3's in the red cells would have to be true, right? So watch what happens in block 5 when I enter those two candidate 3's as the solutions to those two cells. You see, it wipes out all the 3's in block 5, which is another impossible situation. So again, this proves that the 3 in the yellow cell cannot be false and must therefore be true, which means you can immediately fill it in as the solution to that cell. All right, let's look at one more hand-drawn example, and then we'll look at a couple of real examples of this phenomenon, and then we'll wrap it up for today. Okay, here in this diagram, up in block 1, we have two candidate 8's, so we can see them as a right angle this way, but that doesn't get us anything. or we can see it as a right angle this way, and now we have an empty rectangle. So notice that we have two candidate A's in the blue cells, and they both form a conjugate pair with the candidate 8 in the yellow cell. So we have two conjugate pairs coming off that empty rectangle in block 1. So we know from the last example that we can immediately place this candidate 8 as the solution to that cell, and it will eliminate the 8 from those two blue cells as being false. But let's look at this one other way. Remember I said when there are two candidates in the empty rectangle pattern, we can see this as a turbo fish. So let's take a look at that. We have two turbo fish because this is a dual empty rectangle. So our first turbo fish starts here, and there's a strong link, and then a weak link over to this 8 in row 3, column 7, and then a strong link down to this 8 in row 7, column 7. So this 8 over here can see both endpoints, and that will be false. And then we do it the other way, and the turbo fish starts here, and that's a strong link, and then a weak link down to this 8, and then a strong link over to this 8 in row 7, column 7, and then we know that this 8 must be false. So again, we proved that these two 8s, these two candidate C's, where they were candidate A's, but now they're candidate C's, they are both false, and you can enter the 8 into this cell as the solution to that cell. Okay, let's take a look at some real examples and some real puzzles. All right, in this puzzle, let's take a look at candidate 2, and we'll light them up. And we've got an L in block 1. Right there. There is an L. And we've got two conjugate pairs coming off of this. The first one is here in row 6, because that's in the same column. Our candidate A in the blue cell is in the same column as the empty rectangle. And then the other candidate A is in the same row as the empty rectangle, and that leads to a conjugate pair in column 5 to that same candidate B in the yellow cell. Okay? So we know that we can immediately solve the yellow cell for candidate 2. Boom. And that eliminates the candidate 2 from the two blue cells, and it solves the cell in row 6, column 5. All right, let's go to the next one. All right, here on candidate 9, in block 5, we have a right angle. And we have a conjugate pair in row 7 that goes from here to here. And we have a conjugate pair in column 8 that goes from here to that same yellow cell. So there's our two conjugate pairs coming off the empty rectangle. That's a dual empty rectangle. And when we see this, we know that we can immediately solve the yellow cell for our candidate, which is 9, and that's the solution to that cell. Okay, I realize this may all seem a little overwhelming at first, but really it's not that hard. You'll get the hang of it in no time. You'll see. Okay, that's it for today, so let's go back outside and finish up. Thanks for watching. Wow, that was a long one, huh? Thanks for toughing it out with me. I didn't mean for it to be so long, but one thing just led to another, and I wanted to make sure that I didn't leave anything out. Empty rectangles are always all over the place in almost every puzzle, so you should definitely keep an eye out for them. Just make sure you know how to identify all the 33 shapes. That's the most important thing. Most people probably switch this video off about halfway through or sooner. So if you're still here watching and listening to this marathon lesson, then there is hope for you. You are one of a select few who have the attention span, the willingness, the desire, and therefore the true potential to become a Sudoku master, which by the way can apply to either a man or a woman. The term master is gender neutral. Just for the record, there will not be an adjunct to this video. I think we covered everything here. In the next lesson, we will take a close look at bi-value cells. We're going to talk about all their interesting characteristics, versatility, and usefulness, and we will also examine many of the solving techniques that employ them. They are one of the most powerful and important concepts in Sudoku, so I think it's worth dedicating an entire video to them. It will be very interesting, I assure you, so I hope you will join me for that. In the meantime, be well and be happy.